Welcome to another one of our ANEMEL webinars. Like you all probably know, because you subscribe to the newsletter and you probably joined us thanks to one of our links. ANEMEL is a European project funded by the European Innovation Council. We try to make clean hydrogen from dirty waters, and we organize a series of webinars with speakers within our consortium and speakers in industry, speakers in academia, to discuss the latest trends, the latest discoveries in the world of green hydrogen and water electrolysis. And today we're here with one of the PhD students in the project ANEMEL. We've got Arthur, who's based in TU Berlin, and he's gonna deliver a presentation on ionomers and how they could improve the efficiency of water electrolysis. Before we do that, let me just give everybody a quick reminder that thanks to the infrastructure on YouTube, we get to have a Q&A after this. So if you have any questions for Arthur, please just leave them in the chat on YouTube. We'll read them after the presentation and pass them on to the speaker. And I think without further ado, yeah, I'm very happy to have Arthur here with us. I'm really looking forward to the presentation, although I got a little bit of a spoiler sneak peek yesterday already, but it's a very interesting presentation. It's very exciting results. So Arthur, the floor is yours.
Perfect. Thank you very much, Fernando, for the very nice introduction. So good afternoon, everyone. It's my pleasure to present this seventh session of the webinar series from ANEMEL. So I will present today the latest publication that we had in partnership with Thévenot, so a partner from the ANEMEL project. And this presentation is about Ionomer interface layers enable efficient AEM water electrolyzer operation at low pH. So before diving into the technical details, I would like to begin by setting the broader context for this work. So developing green hydrogen technologies is critical to increase the low emissions hydrogen demand. So the graph that we see on the left, we'll just put the laser pointer right here, perfect. So this graph that we see over here from the International Energy Agency, and more specifically from their Global Hydrogen Review from 2024, shows the low emission hydrogen demand by sector in 2023 over here, with estimations for 2030 in the stated policy scenario over here, and in the net zero emissions by 2050 scenario. So as we can see, by 2030, with the stated policy scenario, we should expect around 6 megaton per annum hydrogen, which is far away from the 65 megaton per annum of hydrogen with the net zero emission scenario. So how come we see such a drastic difference? Well, low emissions hydrogen is more costly than the hydrogen from unabated fossil fuels, which prevents its adoption among most existing hydrogen users. Therefore, this highlights the need to develop efficient green hydrogen technologies with reduced costs. Among the green hydrogen production technologies that we have, one of the newest one, and that is maybe the most promising one, would be the anion-exchange membrane water electrolyzer, and also known as the AEM water electrolyzer. So it's actually the combination of a traditional alkaline water electrolyzer, which uses non-precious catalyst material, and of a PEM, so a proton exchange membrane water electrolyzer, which uses a solid electrolyte polymer membrane, which gives us high efficiencies, so from 70 to 80%, and high hydrogen purity, which is above 99.9%. And so this combination gives us the AEM water electrolyzer, so therefore with reduced carbon footprint as we use sustainable materials, and with high efficiency and purity. The electrochemical half reaction that occur inside this electrolyzer are actually the same as the alkaline water electrolyzer, as we are in alkaline medium. So what happened exactly? So your water molecule at the cathode will be converted into hydroxide ions and into hydrogen. So we keep the hydrogen because this is what we want. These hydroxide ions will then travel to the anode through the membrane to then yield oxygen and water. And this water molecule will then go all the way back to the cathode to reiterate the cycle. The current electrolyte that we use for this kind of electrolyzer is 1 molar kWh. So it's still way less concentrated than for alkaline water electrolyzers, so the traditional one. But it's still highly concentrated enough to have risk of corrosion of your cell components, which will induce naturally reduced lifetime and increase maintenance costs. So a solution for this would be to switch to low alkaline or neutral water feed. Of course, this will also give new challenges, such as reduced connectivity, as you don't have as much ions as in the 1 molar kWh electrolyte. Also, you will have catalyst leaching from the MEA, which will induce increased overpotential. But before going any further, what is exactly an MEA? Well, an MEA, also the membrane-electrode assembly, is I would say, an association of different components of your electrolyzer. We have over here a very nice scheme that was made by a former colleague of mine from my work group, that actually shows a simplified scheme of water electrolyzer, an AEM water electrolyzer. And so as you can see here, it's inherited from the sandwich type design from the PEM water electrolyzer. So as we have on the outer side the bipolar plate with the flow fields to have the circulation of the fluids, so the liquid and gas. Over here we have what we call the porous transfer layer and the catalyst layer. So then together will be the electrode actually. In the center we have the anion-exchange membrane, and on the other side we have the other electrode and the other flow field with the bipolar plate. So as one may have guessed, we have then on one side the cathode side and the other side the anode side. The MEA in all this is simply the combination or the association of your anion-exchange membrane, and of your cathode. In our study, we wanted to use benchmark materials, so mostly materials that are available commercially, in order to have reproducibility and to then have cross-laboratory results to have better comparison between studies. And this is especially the case for our membrane, so which is the Scandinavianz X3750T from dioxide materials, and of an important component we study that will be the Ionomer. So also that is the Scandinavianz X89 Ionomer from dioxide materials. So what is exactly this Ionomer that I just described right now? Well, it's a very important component for this study. It's actually the central component of this study. So an ionomer is a polymer. A polymer is a very long molecule, like a chain, with repeating building blocks, with these repeating units. And the difference between an ionomer and a simple polymer would be that on an ionomer you have indeed mostly neutral groups, neutrally charged groups, but also and mostly ionic groups, so charged groups, either positively or negatively. In our situation, with this Scandinavianz X89 ionomer that we are using in this study, we have as a neutral group this styrene group over here, and as an ionic group, we have this one, which includes an imidazolium group, so with this positive charge that we see right here. What are the roles now of this ionomer? What can we do with this? Why do we need this actually? Well, traditionally, the ionomer was used as a binder to apply your catalyst layer on the PTL and avoiding catalyst detachment. And this is especially the case for powder catalysts, such as the one that we use at the anode, that is called the nickel-iron layer double hydroxide, also known as nickel-iron LDH. So how does it work exactly? How do we prepare this? Well, our powder catalyst will be mixed with the solvent and with the ionomer, and that will give us what we call an ink. This ink will go in this airbrush, as we see here, and we will simply hand spray it on our PTL that is right here. And yes, it's the exact same airbrush that you would use for art purposes, such as painting miniatures, in case you are into it. And the results, after the spraying, we obtain this electrode, this anode in this specific case. And the bright yellow color that you see over here is actually the catalyst layer that is typical from the nickel-iron LDH catalyst before its electrochemical activation. Once you actually activate it in your system, it becomes fully black. The second role now of this ionomer is an ion transport enhancer. So thanks to actually its ionic groups, it will help the transport of the ions that are oppositely charged. So in our situation, for example, our ionomer has positive charge groups, so with these imidazolium groups. As it's positively charged, it will help the flow of negatively charged ions, also known as anions. And as we are in alkaline medium, we want to enhance the transport of the hydroxide ions, these OH- ions that are flowing through the system. So now, beginning the actual study, beginning the actual results now. So we very first to have a scope to understand what's exactly going on when you go to lower pH. We tested this benchmark AEM water electrolyzer under the low pH conditions. So at 1 molar kWh, pH 14, with 0.1 molar kWh, pH 13, and then 0.01 molar kWh, pH 12. So the activity, the performance is actually shown over here. So if you are new to this field and you don't really know how to understand this, this is actually the voltage of the cell plotted as a function of the current density. What is exactly the voltage of the cell? It's the energy that you will give to your system in order to have the movement of charged pieces. So you give this energy on the system, so this voltage, and this voltage will then, by giving this tension, you will have a flow of charged pieces. So it's electrons, as you may know it through your electric sockets, for example, when you plug things in at home. But in the electrochemical world, it also implies ions. And this is what's most important for us. And why is it called current density? It's simply because it's the current per square centimeter. It's simply a metric to have better comparison between different studies, basically. And as you may have guessed, the lower the voltage is required to obtain a certain current density, the better it is, because then it means that you have a higher efficiency. What we see below now here is what is called the high frequency resistance. And these values are actually obtained through an electrochemical technique called the potentiostatic electrochemical impedance spectroscopy. This technique is allowing you to deconvolute the different phenomena that occur in your system. But of course, it's difficult as the electrolyzer is a very big system with multiple layers and multiple interfaces. And therefore, it's always a bit difficult to deconvolute this when you have a true electrode setup, as we have here. And therefore, we stick to the HFR, and this HFR gives us the ohmic resistance of your system. So what is the electrical resistance for your entire system? So as we see here, the pH14, in the pH14 electrolyte, we have, well, very satisfying results that are even industry relevant, as we have 1 amp per square centimeter below 2 volts, so which is, I would say, the minimum requirement to go to the industry. But then, if you go to pH 13, so decreasing to 0.1 kWh, you have a drastic increase or drastic loss of performance actually already. And then even going lower to pH 12, you have an intolerable performance drop. You cannot do anything with this. You can just discard it. I mean, it's, yeah. Regarding the resistance, we can also see that the ohmic resistance is actually increasing. So of course, there are multiple explanations to it, so it's difficult to really explain precisely why without any additional analytical techniques. But a very possible hypothesis is that as we get scarcer and scarcer in OH-, so in ions in your system, then you have a higher ohmic resistance. Now we try to do a stability test afterwards. I mean, if we may call it a stability test, as it's only 20 hours. And we saw that for the pH 14 and the pH 13 test, we still had, I would say, reasonable performance loss after 20 hours. But for the pH 12, we have an enormous 25.8 millivolt per hour, which is gigantic. I mean, saying you can just discard it at that point, you know. So this raises the need to optimize our system we need to optimize the system to go lower in pH. So the idea then, as we are scarcer in OH- ions content, was to use this ionomer in order to make better the transport of these OH- ions. And our hypothesis is that it's actually important to do it on the cathode side, actually. And this is actually a critical side, to do it on the cathode specifically, and not just on the anode, as we already have some ionomer on our anode side. And we also see in the literature that also they explore a lot on the anode side. Only a few had some trials on the cathode side. And therefore, what we wanted to do through this study was to thoroughly study the impact of different ionomer architectures on this cathode catalyst layer. So in this study, we will see three different architectures. So the first one that you already just saw right now, which is the ionomer-free configuration. So no ionomer on your cathode side at all. As we can see from the simplified sheen, we show the cross-section of the NDA on the cathode side. What you see below is actually a top view through microscopy of your catalyst layer on the cathode side, which is actually a real image this time, it's not just a sheen. Then the second architecture that we will look at is the one that is also traditionally found on the anode side, and the one that we also use on our anode, but for different reasons. So on the anode, we use this one for the binder properties, but here we want to use them for the OH- transport properties. And this is named, so then the ionomer in the catalyst layer. The ionomer is with the catalyst layer inside. And this is a resulting morphology change on the cathode catalyst layer surface. Then the last ionomer architectures, which is last but not least, is the ionomer top layer. And this time here, we will put this ionomer on top of a catalyst layer as an interface over the catalyst layer between the catheter and the membrane. And this was the result after spraying this layer. As you may have heard, I use the word interphase and not interface. And it sounds nearly the same, but the meaning can be a bit different, and it's actually essential to understand the difference for this study. So by interface, I mean a two-dimensional frontier between two entities. Meanwhile, an interphase, by interphase, I mean a three-dimensional phase that will be between these entities. And for example, this ionomer top layer would be the interface, as we have a phase between the catalyst layer and the membrane. So now diving a bit into the performance of our system. So as we can see, first with the ionomer in the catalyst layer, but even with very low ionomer content, it improved significantly the performance of our system. So with only 0.02 milligram ionomer per square centimeter, we already gained 1 volt, which is gigantic actually. And we also see that increasing the ionomer content increases actually the performance of the cell slightly. And therefore, the hypothesis for this would be to say that the ionomer is acting as an ion pathway, and therefore increasing the transport of these OH- ions from the cathode to the membrane. And now, regarding the performance with this ionomer top layer, so in pH 12 as well, we see that similar to the ICL configuration, only with very thin layers, so also 0.08 milligram ionomer per square centimeter, we already have also a drastic performance increase. And we see that increasing the ionomer content also increases the performance of the cell, which is very interesting actually. However, we see that having excess of ionomer can be seen as a thick interphase, which will increase the cell resistance and also induce the deterioration of your activity. And this shows that the OH- transport at the interface, so at this two-dimensional frontier between the cathode catalyst layer and the membrane, plays a critical role. After having this activity test or this performance test, we wanted to have a stability test of the ICL and the ITL interface architectures. And to first see if it would be collapsing just as with the ionomer free version, or whether we would see different behaviors. And thankfully, we saw that fortunately it did not collapse, so we were quite happy about this. And we also see that the behavior is actually quite interesting, because we see that for this ICL, so over the 80-hour test, we see only a very slight increase in degradation rates, while for the ITL, we see a slight decrease of the degradation rate over the 80-hour test. And also, during this test, each 20 hours, we also measure the ohmic resistance of the entire system to see how it will evolve through the stability test. And we saw that we had only a low increase of the ohmic resistance over the total duration of the test, which is a good sign and shows also the benefit from using less oxidative ionomer, the benefit from using lower alkaline conditions that will give you less oxidative ionomer degradation, as this is an issue that we can find also when using highly concentrated alkaline electrolytes. And naturally, further investigation will be needed to properly explain the different behaviors between the ICL and the ITL. After having these interesting results at pH 12, we then wanted to have these mechanistic insights into the role of the ITL interface. And therefore, as we tested here these architectures under scarce OH- medium, we then wanted to check in abundant OH- medium, so back to pH 14. What happens? How do these architectures behave once you have this abundant OH- medium? Will it be worse, not changing anything, or better for some reason? Well, starting by the ICL, so the first one that we tested overall for this study, we see that at a lower color density, we have a worse performance compared to the ionomer-free cathode. And actually, this can be explained by the fact that the ionomer ionic connectivity has a lower, the ionomer ionic connectivity is lower than the 100 kWh electrolytes, and therefore will have this lower performance. However, at higher current densities, when you have a bigger flow of these charged pieces, the enhanced porosity of a catalyst layer, so from the incorporation of the ionomer, can then explain the better results that we obtain over here. And then regarding the ITL this time, we also see a performance benefit over the entire voltage window, even if it's highly conductive 100 kWh electrolyte. And this supports the hypothesis of the Ionomer top layer that is facilitating a microscopic ionic pathways between the catalyst layer and the membrane. Now, so from these results, this brought us to this hypothesis actually that we have about this Ionomer top layer that is actually acting as a non-rigid polymeric interface, and therefore the uneven catalyst layer surface will become smoothly linked to the membrane surface. And therefore this will be supporting the ion pathways between the cathode catalyst layer and your AEM membrane. And here we can see over here that even though it's still a small increase compared to small benefits of performance compared to the pH 12, it's still quite noticeable as we are in very abundant OH- medium. So now, as a takeaway and future focus, I will quickly summarize what we saw today, giving also a quick takeaway and then our future focus for our group. So first, I showed that in pH 12 AEM water electrolyzer, using an ionomer-free catalyst layer on the cathode would give bad results, due most likely to poor OH- transport. Therefore, to counter this, we investigated two ionomer architectures, so the ionomer in the catalyst layer and the ionomer top layer. We saw that using both of them, so if on each of them, I mean, it increases a lot the performance of your whole system, and the ionomer top layer is slightly better. But then afterwards, we wanted to check the mechanistic insights to understand the role of this ionomer top layer through the system. And we actually saw that even in abundant OH- medium, the ionomer top layer was actually still superior than the ionomer-free catalyst layer. And therefore, this led us to the hypothesis that the ionomer top layer is actually optimizing the interface, so this two-dimensional frontier between the cathode catalyst layer and the membrane. This brings us to our main takeaway from this talk, which is that managing the ion transport at the cathode catalyst layer and membrane interface is key to improve your electrolyzer performance in low alkaline environments. Our future focus now would be to have deeper understanding of the ionomer distribution and also on the layer properties after applying this ionomer, such as the thickness or the porosity, which can have a great impact into the performance increase. And then the development of advanced ionomer top layer design, this time for pure water feed. So this time with no OH- at all in your electrolyte. So thank you very much for your attention. If you enjoyed this talk, I highly recommend you to have a look at the original paper where you will find all the technical details that I may have not talked about today. And if you have any question, it will be my pleasure to give an answer. So Fernando, I give you back the speech.
Cool. Thank you so much for a very, very nice presentation. Also for those who are not that much into the technical details, we also have a blog post on the ANEMEL webpage about this very paper. So you want to go to anemel.eu. We've got a very nice story explaining the results of the paper. We have some questions from the audience, but I feel like they're very technical. So before we go into those, I'd rather have like a quick chat with you about some like non-technical aspects of the presentation. Because at first when I got the title to advertise the presentation, I saw like low pH electrolysis, and then I saw it was pH 12. I was like, that must be wrong. But you've explained very clearly how it's way lower than the usual 14. And you also explained very clearly how pH is really a compromise, because if you actually lower the pH, you get fewer ions, and then if you get fewer ions, obviously electrolysis takes longer and is more difficult. So how low do we really, how low can we really go in this time to avoid corrosion and at the same time keep electrolysis flowing at a good pace that's competitive? What do you think about that?
So if I understand properly, the question is what would be, I would say, the lowest pH you can go for an AEM electrolyzer to still have an efficient performance?
Yeah.
Okay, so I mean, in that situation, we tested at pH 12, so 0.01 molar kWh, in order to have a sort of transition between the very highly concentrated 1 molar kWh and the pure water feeds. And therefore, for us, this was kind of like a transition, a milestone. And also, it was also for us to have kind of like the gradual transition, also going through pH 13. And that's already quite a huge decrease of pH because it's already divided by 100 times. But however, for performance, you could actually technically already go down to pure water feeds as long as you optimize properly your system, actually. So this is why we saw here, I mean, we are only using, of course, these benchmark materials that we saw here from pH 12 that already gave very interesting results. And also actually through ANEMEL itself, actually we are still working on also on going to pure water feeds, which is absolutely doable by optimizing properly your system and Ionomer content and also Ionomer architectures, because the idea is that this Ionomer will simply enhance the transport of its OH minus by in sort of way replacing the conductivity of that you had already with your 1 kWh originally. And so therefore, by having an optimized Ionomer content, then technically you can have a very efficient system that works in pure water, and therefore at the same time having it efficient, but also with less corrosion.
Yeah, and I have another curiosity because you mentioned miniatures and painting with the spraying, but I think the idea of ANEMEL and maybe the later projects that follow up will be the opposite of miniatures. We want this to go big. So I'm assuming the spraying techniques could be easily translated into industry with, I don't know, electrospinning or spray coating techniques that you could actually use in big scales, and that's why you use this in the lab?
So actually in the lab, so indeed we use this hand spray originally because it's for more, I would say, screening tests, more quicker tests at small scale. If you want to increase the scale, of course, you have some, I would say you have some apparatus that are made, some equipment that are made to have it automated. So we already have an automated sprayer actually in our work group. We use it especially more for platinum to test, to, I would say, apply platinum catalyst layers on some PTL. So that's why I don't use it for this study as I use a non-PGM anode catalyst. However, yes, in the industry you have these equipment that allow bigger scale. And of course, that's the point with ANEMEL. And also for this nickel LDH that I was testing here, it was only a benchmark. And we are working actually with ANEMEL to simply use new catalysts that we received now from some of our partners that showed very promising results using a scalable synthesis and anode preparation techniques.
Yeah, I think that also highlights something that was very present in your talk, the collaboration between the different partners, because we've got people building the catalyst, we've got people doing the membranes, we've got people doing the ionomers, and then when it all comes together to do the MEA, the assembly, that is the very nice work, all together. I have a little bit of a trick question before we go into the technical ones. Because one of the main ideas behind ANEMEL is, of course, to study the LCA sustainability, recyclability of the components. But at the same time, we're talking here about sort of intertwining a mesh of ionomer into the catalyst, into the membrane possibly, and then maybe, it's a little bit counterintuitive how this compromises the improvement in efficiency and at the same time may complicate recyclability? Are you looking into how to get the ionomer out if we want to recover the catalyst or if we want to recycle the electrolyzer in the future? Is that something that's envisioned in the study?
So in our situation right here, so our focus is on the NA performance, more specifically for our work group. However, in the ANEMEL project, we have a work package specifically dedicated to the life cycle assessment. Then I'm in close contact with them actually to give them all the details regarding our electrolyzer system. So from very detailed actually, from the thickness of our PTLs to the content of our ionomer and how we use it exactly, so that then they can have actually proper estimations about the recyclability and all life cycle assessment from cradle to grave of our system. So to summarize very quickly, we are focused on more on the performance and the efficiency of the system, and then in collaboration with the work package 5, so which is for life cycle assessment, we can then have this interaction to see how we can also improve our system to have it the most sustainable as possible.
So it's like a work in parallel to make sure that we're not introducing anything more toxic or like more difficult to recycle than we already have. Yeah. So I had a few questions about the components and how they go into the catalyst layers, and but they seem to like there's a lot of overlap with the specific technical questions that we got in the chat. So I'm gonna move to those. We've got someone that goes as SK asking if you could confirm that the processes that you've shown were done with a KOH feed on both the anode and the cathode, or with the identical concentration of KOH, or were you using a dry cathode without the basic media?
So in our test, we use a symmetric feed, which means that we put the electrolyte in both anode and cathode at the same time, and also using the exact same concentration. So for pH 14, pH 13, and pH 12, we have the exact same concentration of KOH in both sides. So example for the pH 12, it would be then pH 12 KOH on one side and pH 12 KOH on the other side as well. However, the dry cathode configuration is very interesting as well and can be tested and can be part also of our future work to improve furthermore the system, especially when going down to pure water feeds.
Cool. And then I hope that that answered your question, SK. If not, feel free to add a follow-up in the chat. We've got Clara Choi asking also about the ITL that you described. I don't know if maybe we want to move a few slides before and bring those back again. Because she was saying, is the ITL free of ionomer within the catalyst layer? Or is it the ionomer interface with pH interface ionomer in the catalyst layer? So could you clarify where exactly the ionomer is in this ITL mix that you showed?
So if I understand properly the question was whether we observe some ionomer inside the catalyst layer despite having it spread over it. Is that so?
So the question is the ITL free of ionomer within the catalyst layer? Is there any ionomer in the catalyst layer, or is the ionomer interface and the ionomer in the catalyst layer?
Okay, I see. So for the ionomer top layer, indeed. So it's possible that, I mean, we spread on the surface, that is for sure. And originally there was no ionomer at all inside the catalyst layer. But it's indeed interesting because for our further studies to understand better the porosity and thickness of our system, it can be interesting to see whether while spraying, some of the ionomer penetrated a bit deeper and therefore which would not be pure surface, but also maybe a tiny bit more into the bulk. But hypothetically speaking, normally there should be non-ionomer inside the catalyst layer. That would be interesting indeed to understand better maybe the surface properties of the system.
Yeah, and then the same person, Clara, also has some questions. To be fair, I did have this question when I saw the first scheme, the one you showed by your lab mate who had shown the different layers. Is it like, have you tried the ITE approach in the anode and the cathode, just the anode? Like how many of the layers have you actually tried to improve with them?
We actually did right here. So I prepared this backup slide. I hope that will answer the question. So we wanted indeed to have a little trial of the ITL on the anode as well. So we first need to know that we already have some ionomer inside the catalyst layer of your anode for the binding properties. But of course, it will also enhance the OH minus transport, even though that was not the main purpose of it. But when we apply this ITL on the anode, and therefore no ionomer on the cathode at all, we see that we have maybe a slight increase after putting a certain amount of ionomer, which is actually a bit surprising for us, as we saw that we had a way worse performance when applying a bit less and then having it directly better afterwards. So it was a bit surprising to us to see this trend. However, we saw that there was barely no improvement at all actually in that regard. But then we wanted to, and also we need also to check also the range of the voltage that is still extremely high. But however, then we wanted to try on both the anode and the cathode because perhaps with this slight increase, maybe it would still increase a little bit more, maybe the performance. But we saw that unfortunately, no, we still have it a little bit worse. And therefore, this maybe means that as we already have then the ionomer on the cathode side, then that's already boosting the OH minus. Then having more ionomer on the anode side is actually not beneficial anymore, as the ionomer already has plays its role already on the anode side to transport the OH minus over there. So I mean,
either you're like a very good actor and really, like you were really happy about that question, but it looked like you had been prepared from the audience because you had the right answer ready after the presentation. So it's really cool that happened because it means A, we've done quite interesting work in ANEMEL, and B, the audience is really keen on the results and learning more about that. But I mean, you show like genuine happiness from getting that question from me. But I'm gonna assume you don't know this Clara person asking behind the screen. We have another question from SK that I sort of skipped before because it seemed a little bit unrelated to the composition of the electrodes, but he did ask. I mean, they asked if you studied or plan to study the effects on hydrogen crossover from the modifications of the ionomer, and what were the results if you did.
Well, first of all, thank you for this question because it's a very important question to ask, especially when you go upscale. So in our specific test right here, we did not check the hydrogen crossover. However, if we do, because it was more, I would say, performance-oriented test, and also the stability test is very short, so only 80 hours. However, when performing a longer stability test, it's essential to check your hydrogen crossover because you do not want when you are in an industrial scale to have hydrogen going on the oxygen side because otherwise it's dangerous. Actually, you could have some accidents if it's happened at a bigger scale. So therefore, for this specific study, we did not check it as we're still at a small scale with shorter durations. However, when going through longer stability tests or going into bigger scales, then yes, it's important to check the hydrogen crossover. Yes, absolutely.
Cool. So yeah, both people who asked the questions are thanking us in the chat. Can't read the full messages, but they're both very happy that you answered the questions, and they actually say that the work is really interesting. Thanks for sharing that, and thanks for preparing the backup slide. We don't seem to have any other questions from the audience, so I think I should also like thank you, Arthur, again for your wonderful presentation and for your time preparing this and giving the webinar. It's been great to have you here today. And just a quick couple of notes for the audience. I know you're all big fans of ANEMEL because you keep joining the webinars every month, and it's great to have you here on YouTube. But just a quick note that not only do we have a blog post on the paper by Arthur and the team in TU Berlin, which is easy to read, easy to access in anemel.eu. But then also there's plenty of materials in anemel.eu about the project and about some of the things that were actually mentioned during the presentation. I remember a slide from Arthur comparing AEM with the rest of the electrolyzers in the sort of competition for water electrolysis. We've got a dedicated feature post on the differences between different electrolyzers. So feel free to check that out. And of course, feel free to check out the rest of the materials, the infographics, the videos we've got about the project. I think it's really interesting to see what our researchers are doing. Thanks again for joining the webinar. Thank you also to the European Innovation Council for funding the project. It's always a pleasure to work in this type of blue sky research to see if we could actually make something as difficult as seawater electrolysis happen. And if you want to keep in touch with ANEMEL, not only do you have the webpage, but also social media. You've got a newsletter, so please subscribe. You get the link at the end of this presentation, I think, and then also it will probably appear somewhere in the chat. Look at me, I'm like a YouTuber pointing places without knowing where I'm really pointing. But the link should be there somewhere. Otherwise, you can go to our webpage and check it out. It's very easy to find. It's anemel.eu. Find us on Twitter, on LinkedIn. And yeah, thanks again, Arthur, for a wonderful presentation.
My
And
pleasure.
yeah, see you very soon, everyone, in our next edition of the ANEMEL webinars.